Not sure exactly where this is in the textbook. Although we'll look a little deeper into. So the makeup of our power supplies, and we'll talk about what we call the switch mode power supply later on. But we start off with usually we start off with a transformer, right? So this will be, and then what comes next? What comes next? After the transformer. The rectifier. Right? And this would give us either half wave or full wave. And then if we're working on a regulated power supply, what would come next would be the filter. Of course, what does the transformer do? Well, a power supply, it's going. You're right, but it's going to step. What'd you say? Don't step up. Don't change the power. Don't change the power. Steps up the voltage. If it steps up the voltage, the current goes down for that wattage, right? If it's, Now I tell y'all that we had when we did our interviews, one of our interviewees did the difference between AC and DC, and he made that statement right there, and he didn't get the job. Huh? What's that? Yeah, we had a group of, I think 6 or 7 that was in the hiring committee. So, and one of the things that they needed to do was to make a presentation just to see how they handled themselves and moved. And we had one guy that did a presentation on the difference between AC and DC, and he didn't know the difference between AC and DC. He didn't know. And that's one of the things he said. He says the transformer, you step up or step down by power. That killed him right there. So he didn't know. So what's the advantages of AC over DC? Why do we have 2 different currents? DC would be more efficient to transmit, but we can't transmit it. And why? I mean, we just can't do that easily. It can be done. So what is one of the big, AC's got 2 big advantages. One of them is the main advantage. And then we have another one that works with motors. But what advantage does AC have over DC? So what is Alabama Power selling you? Power. And they're trying to get that power from their plant to your house. And they're trying to send it through wires. Now, what's the problem with wires? Yeah, they have an R. So V is equal to I times R. There's no such thing as a conductor that has no R. Right? You understand that? So V is equal to I times R. So what happens in transmission, they call it line loss. This is how much loss you get in the lines just trying to get it from the power plant to your house, right? And here in this college, we're on TVA. Where's our power plant? Where's TVA's power plants are? All up in the Tennessee River, up in the Tennessee Valley, right? You understand that? So that's up in North Alabama, and they're trying to get that power down to Lawson State Community College, and they're trying to do it through wires. Okay, you'll understand. So the big formula is here. Power is equal to what? V times I, but that's not the big thing. This is I is equal to P over V. And I'm trying to sell you power. So if I can make that voltage real high, then what happens to I? It drops. So the higher I can make that voltage, the more power I can send you at a lower current, right? You understand? So if I could step that up to 750,000 volts, which is common, I could send you 750,000 watts of power with 1 amp of current. Y'all understand that? Now, if I could step DC up to 750,000 volts, it would be more efficient, because the problem we have with AC is we have this dang thing called X of L and we have this thing called X of C, which basically varies with frequency. So if I could get 750,000 volts of that DC, it would be better to transmit. But the problem is I cannot easily step what? DC up and step DC down. We can step AC up and AC down by using what we call mutual induction, right? You understand that? So we know that every time I put current through a wire, it generates a magnetic field. If that magnetic field strikes another conductor, it will induce a voltage into that. So we have these things called transformers. So we can change the turns ratio, and we either can step the voltage down or we can step the current up. No, I don't know that. I'm up here just a drawing. I don't have, even though my grandchildren thinks I do. So a lot of times I put my glasses on like this. Yeah, so I don't lose them. So I is equal P over V. So the big advantage of AC is that we can step it up for transmission and then do what? Step it down for safety. But theoretically, if I turn on a 100-watt light bulb on my house, Alabama Power or wherever you got generates 100 watts. Transformers don't change watts, they change volts, right? You understand that? So they don't change power, they change voltage, which is causes the current to either go up or go down to get that power to your house, right? You understand? So higher wattage, higher voltage means I can use smaller conductors. Or instead of using copper to transmit it, I can now use aluminum, right? Which is almost a semiconductor. So aluminum has 3 valence shells. To be a conductor, 3 electrons in the valence shell. To be a conductor, considered a conductor, is between 1 and 3. So aluminum is almost a semiconductor. But it's what? It's a lot cheaper than copper, and also it's a lot lighter, right? You understand? So it saves all over. So we keep stepping it down. The closer we get it to ground, and the closer it gets to us, we start stepping it down till it gets to our house. And we have 2 voltages at our house. We have 120 and we have 240. All your high wattage loads runs off what? 240. They are designed to run off 240. All your lower wattage devices run off 120. So we start off with a transformer. So the transformer is going to step the voltage up or step the voltage down, but basically this guy is what's going to set your output voltage. So if you need a lower output voltage than your input voltage, you're going to use a step down transformer. If you need a higher output voltage than you do an input voltage, you'll use a step up transformer, right? That makes sense. So we have 208 here. The robot, even though it runs off DC, the ABB robot, even though it runs off DC, needs 440. So what do we have to do? We have a step up transformer for both the ABB and the big families. They run off 440. So we got step up transformer. So you can't say they step it down. They're going to step it. But that transformer sets what? It actually sets your initial output voltage. Then we have the rectifiers. What do our rectifiers do? So this converts what? AC into pulsating DC. Are we okay? Then what does our filter do? It converts pulsating DC into unregulated DC. And what do we mean by unregulated? Huh? Right, it means it will try to maintain a constant output even though you put varying loads on it. So it's like your car. You can If you put a meter out there on your battery, which is you're looking at the regulator, you turn on your lights, you turn on your air conditioner, and all that kind of stuff, it should maintain a what? The same output. Now in power supplies, we got another thing it's got to regulate. So it not only regulates this, it also tries to regulate what's going on here. So if I design something around 120 volts and then I go home and I only get 115, if I don't design around that range, then that's going to give us a problem, right? So even though my input varies, even though my AC input varies and my output loads are varying, our regulators are supposed to take care of that. So what happens is that the output of that filter will vary if your AC coming in does what? Varies, or if your load varies. And of course we get that thing called the ripple voltage, right? And then eventually we're going to add a regulator. What's the regulator going to do? It's going to regulate. It's going to try to maintain a constant output. Well, you put different loads on there, but it's gonna have set limits, right? You understand? If you design it around 5 amps and you try to get it to run 30 amps, it's gonna go out of regulation. Or if you design it to as a minimum voltage of 90 volts, and for some reason your power drops down to drops down to 80, then it's gonna go out of regulation. And a good example would be your cruise control on your car. It'll maintain speed. It'll maintain the speed on a slight incline, but if you go up an incline like that, then you've exceeded what your car can do, right? You understand the speedometer will actually start dropping down. Or if you go down a slight hill, it's okay. If you go down a hill like that, then if you got it set for 70 miles an hour, you might get up to 80 miles an hour because you're out of the range of the regulator can handle, right? You understand? So this is also true for power supplies. So if you ever look at the power supplies, it's going to give you what it regulates guaranteed on the input and what it regulates guaranteed on the output. It usually gives you a maximum current. So this is a switching power supply. So somewhere on here it says this guy right here will handle an input anywhere between 100 volts and 240 volts. So if I plugged it into, 300 volts, it's not going to regulate. It's going to be out of its range, right? Or if I get 90 volts in, it's not going to regulate because I'm out of its spec, right? And this gives me a maximum current of 1.8 amps. I'm sorry, that's input. This guy is 2.5 amps on the output because it says 20 volts, right? Everybody understand that? So this is the setup that what we call a linear power supply. We got another power supply out there called a switch mode power supply, which we'll also look at. But these guys are easier to troubleshoot. They're easy to design. So y'all already know some things, right? So we know we got to get a transformer that's going to be able to establish our output. We know we got to get a transformer that has the ability that's rated at a current that I want on my output, right? When you buy your diodes, you got to make sure that they got a breakover voltage that exceeds your input voltage probably by a double. And then you got to make sure your rectifiers can handle the current of the output, right? That makes sense. Filters. The normal filter that we use in a linear regulator is capacitor. And what's the two major ratings on capacitor? So every device has got at least two major ratings that if you exceed, you're going to cause problems. So the two major ratings on a rectifier diode is its breakover voltage and its current. Right? The two major ratings on a capacitor is what? There's no current rating on the capacitor, but that's a good point. That'd be like saying there's a current rating on a resistor. There's no current. Just every device has a temperature on there, but we're looking for the two major ratings. Farads, and then what we call a working voltage. Yeah. The farad is its ability to store a charge. How many coulombs can it hold? Right? You understand? And then the working voltage is where it will break through the dielectric. Well, that's exactly right. If you think how fast it will charge, but how fast if it charges faster, the less coulombs it can hold. Because you think about a bucket. So the smaller, if you're putting water in a bucket at the same speed, and I've got a bucket like this and a bucket like that, which one's going to fill up fastest? The small one. So the smaller the farads, the faster it'll fill up, but the lower capacity it'll hold, right? Does that make sense? The bigger the bucket, the slower it'll charge, depending on how much opposition you get through. It'll hold more what? It'll hold more coulombs. And of course, the formula to figure the charging time is time is equal to R times C. So that's how much resistance you put into series with it. But this is actually 63% because it charges at an exponential rate. Rule of thumb is fully charged is 5 times R times C. And that, if you did all the math, that's around 99%, which to us is good enough, right? But when we charge this guy right here, the only resistance it sees is the forward bias resistance of the diode, which is almost nothing, and then the resistance of the transformer, which is almost nothing. It's some, but we're talking about maybe 20, 30 ohms. So these guys are going to charge extremely fast, right? You understand? Even though they're going to be big capacitors. Huh? Because the resistance is low. And then we transpose this formula. We transpose this formula to actually calculate our ripple voltage. We transpose this formula right here also to figure out what size capacitor I want. So this is the makeup of what we call a linear power supply. Really straightforward, right? And so what we're looking a little bit today is we're going to look in a little bit into regulators. So we got this far, right? We did transformers, we did rectifiers, and we did filters, passive filters. And then next we'll get into regulators. Are we okay? And what chapter? Anybody got the book? Yeah, what chapters does it talk about regulators in? I need to add that. Number 6. That's the older version of that book. So it's in there somewhere. It might be a different chapter. So that one should work fine. When we originally set up the book, this is the one we used. And then for some reason, they went to that big old thing and charged y'all probably 3 times more than that book right there. Yeah, but when I looked at the renting fee, it was not much lower than the dang textbook fee. And I can understand why y'all would want to rent like an English book or something like that, but all my trade books I still have, and I use them even for reference. I used to use them for reference to teach this class, but I don't need it much anymore. So what we do with the capacitor, and by the way, as soon as you add the filter, so originally we came over here, and this guy here, if it's full wave, it gave us this right here, right? And that's where we use that formula, DC is equal to 2V peak over pi. Right? Huh? Yeah. Are we okay? Okay. So it's the same in both books. That's neat. Now, as soon as we add our filter, we never go to common. We never go to 0 volts anymore. So what we end up with is we never see the original charge because it charges up through the transformer. So as soon as we turn power on it, this guy's going to be charged, right? And then from then on, we get this right here. Yeah. We call it a ripple voltage, but it's not quite a sawtooth. A sawtooth would look like this. So this is not a sawtooth, it's actually the discharge of the capacitor. So it comes up here, and then it discharges. It's got a slight slope. And what we're doing, if I come up here, if this is full wave, this is going to be spread out. If we looked at the full wave, it would do this. And then it drops down. And then it comes up and does what? Charges it up again, drops down, charges it up again, and drops down. That makes sense? So the diodes are only conducting right here. As soon as it starts down. So the diodes are only conducting for a short amount of time. So that means we might have a 1 amp diode that we're getting 2 amps out of because it what? Because the diodes are only conducting for a very short time. The 2V peak over pi, this formula's gone. As soon as I add that capacitor, that formula's gone. As soon as I add the filter, we're no longer getting the DC average of an alternation. We're getting DC. We're not getting pulsating DC. So this 2V peak over pi deals with the DC average of an alternation. It does not deal with DC, right? You understand that? And our alternations are gone, right? Everybody understand? So what we look at is we come over here and we look at this guy right here. Let me draw. So what sets our voltage now is these peaks right here. So that would be V peak out, right? It charges up to what we call V peak out. And then it discharges depending on what? The size of the capacitor and the current it's going to have to provide. Does that make sense? That makes sense. And of course our DC, our average DC is going to be right down the center of this guy. Right here. So that's right there. This is what I should measure. Because the negatives and the positive are going to cancel each other out, right? Now, it's never true to go a negative, but it's just like a sine wave. A sine wave is averaged right in the center. So if I was to take a DC, and then I was to superimpose a sine wave on top of that DC, then if I measured it with my meter, if I measured DC with my meter, it'd measure right there. That makes sense? And later on, we're going to do this. When we get into amplifiers, most of our amplifiers don't amplify AC, they amplify DC. So what do we make them look like they amplify AC? Is we superimpose the AC on a DC level. And that's the way transistor amplifiers work. So what we need to do to calculate our output voltage now is we need to come up with another formula. And this is what we was talking about last class. And the formula we're going to use is this guy right here. T is equal to R times C. We don't have to use the 5 because this guy is never going to display. It's never even going to get to 63%, right? You understand? Unless we got big problems with our capacitors or we're trying to overload them. So what's that saying is if I got a certain size C and I got a certain size R, then this time right here, what would the time be if, what would the time be for full wave? What would that time be right there? What would the time be for half wave and what would the time be for full wave? Because that's how long the capacitor is going to run the load. So if I come over here and do full wave, half wave, which would be like this, then that capacitor is going to have to run the load all that time right there. If we're going to do half wave, if we're going to do full wave, if I try to draw these at the same frequency, then my capacitor is going to have to run the load right here. Everybody understand? No, it's a good point. So what is frequency? What is the period of the waveform? It's the time for one repetition. One repetition. So if I come over and half wave rectify this, I get this. So this would be my input if it's running at 60 cycles. This would be my input. Well, that would be a cycle, and that's a cycle too. You understand, because that's one repetition. So on half wave, your time is going to be the time whatever your AC input is in, right? You understand? Now full wave is going to be a little different because on full wave we get this and this. So this would be one cycle of my input. This would be one cycle of my output. Right? You understand? Yes or no? I'm not saying that's the way it is. Go ahead.
So the AC.
This is half wave. This is full wave. So here's the input on full wave. You'll understand that. But how many repetitions do we get out? There's one cycle and there's one cycle. Right? You understand? So on half wave, my pulsating frequency would be equal to whatever I put on the input. On full wave, it's going to be twice whatever I put in. So here, the capacitor is going to have to run this. It's going to have to run that 16.666 or 16.7 milliseconds for 60 hertz. So the airplanes, and this got me in trouble one time, but the airplanes I worked up run at 400 hertz. So right off the bat, that means my capacitors could be a lot smaller in my power supplies because they didn't have to run the load hardly any time at all, right? You understand? Alabama Power, we don't have that ability because what we do is we use what frequency that we're given. The only way we can change the frequency is we could take the so out at U.S. Steel we had an induction heater that tempered the crowns of rails that were going to be used in curves. We ran the induction heater ran at 600 hertz. Alabama Power gives us 60 hertz. So what did they have to do? How'd they change the frequency? Huh? Can't change the frequency with the filter. All the filter takes is filter what's there. So they took the AC coming in, they used that to run a motor. The motor turned another generator, and that generator gave us 600 hertz, and they call them MG sets. And this was long before what we can do with solid state. Solid state was around, but we couldn't do a heck of a lot of power when the Curve Master was first put in. After a while, they came out with some SCRs that could handle hundreds of amps. And so what they did after that is they rectified it and re-oscillated it, right? So that's the advantage of electronics. Of DC, we can electronically control it. A perfect example is this dang function generator right here. So this function generator, how can I change the frequency? Alabama Power gives me 60 hertz. So how can I change the frequency? So how can I come up on this function generator and set whatever dang frequency I want, as long as I'm in the ranges? Electronically, right? We come in, we rectify it, generate a negative and positive voltage, DC voltage, and then we control the negative and positive DC voltage, and now I can do what? I can generate AC from, I can generate it at another frequency. So changing the frequency of your main power source, we can either do it the way they used to do it. How'd they used to do it? An MG set, yeah. So these big old MG sets, and they can handle a lot of current. They were sealed, by the way, and I think they used nitrogen gas. So we couldn't fix them when they broke. So if that thing went down, then they kept a spare there. They had to ship that thing off and get it fixed. That was about one of the only things that left the plant while I worked at US Steel. We fixed everything. But that MG set we couldn't fix. So what we can do with this guy is I can not only do what? I can come up here and I can change the frequency, anything I want to, right? That's all, as long as it's limits. I can make it offset, so I can shift the AC, I can shift the DC, which is pretty neat. So I can come in here and because it's all done what? It's all done electronically, right? You understand that? So AC is not, once we set a frequency, like the power company sets a frequency of 60 hertz, then odds are when we're going to do our power supplies and everything, we're going to do what? Run it on 60 hertz. Unless we come up with what we call a switch mode power supply. And that's exactly what it does. It comes in and rectifies it and then re-oscillates it, right? You understand, at a lot higher frequency. And what's the advantage to a lot higher frequency is that your transformers become more efficient because they're changing faster. And then also our capacitors, our filters can be a lot smaller because they don't have to run the load for a long time. Yeah, a lot of your switch modes power supplies are up in a frequency that we can't hear because they would drive us crazy. So we're talking about 50 kilohertz and stuff like that. So you'll look at a switch mode power supply and it's going to have little old tiny capacitors in there because it don't have to run that load for a real long time, right? So here we're dealing with 60 cycles. But I think there's a place where I asked you about 400 cycles because that's what the airplanes I worked on used to run off of. Huh? Where's that question at? I forgot what it was. I just know it's over there. Oh, it asked for the pulse frequency out for a full wave rectifier running off 400 cycles. Then your pulse frequency would, if it's full wave, it would be 200. I mean, it'd be 800 cycles, right? If it's half wave, it would be 400. So we don't make y'all do any real calculations. It's just a pretty straightforward question. So to calculate our filter, what's the formula we gave y'all? Yeah, but that's where we started off with, but I can't calculate. My capacitor doesn't deal with R. And my capacitor deals with this. So this is the rating in farads, right? And this is the storage capacity. Now, this is the time that we're going to have to come up with. How long your capacitor is going to have to run the load. But somehow in the world, I've got to get V into this formula. I got to get V. Because what we're trying to do is we're trying to calculate this ripple voltage. That's what we're trying to calculate. We're trying to calculate the ripple voltage. Well, we put what Ohm's law says R is equal to. Huh? Let me escape this and get rid of. For some reason, I closed out my PowerPoint. Yeah, so we can come up here and we can say, okay, T, and what's R equal to? Okay, so there it is, V over I times C. Right? And what are we trying to solve for? We're trying to solve for V. So what can we do? Okay? He's looking at the formula sheet. Okay, yeah, we did the other night. So we transpose this around and solve for V. But this is going to be, we're going to call this V ripple peak P. And then we're going to do what? I times C over, I'm sorry, I times T over C. That's it. Somebody come up here and slap me. I times T over C. Or we can use V ripple peak peak. This is easier because here for half wave you'd use 8.3 milliseconds. For full wave you'd use, for full wave you'd use 8.3. For half wave you'd use 16.7. Or we can rearrange the formula where I is equal to C times F. So here for full wave you'd use what? Half wave you'd use the input frequency at 60, if it's 60 hertz, and then for full wave we'd use 120. Yeah, it is, because you don't have to remember the time. All you got to do is, if I put 400 hertz in, you'd say if it's half wave, you'd use 400. If it's, you wouldn't have to figure the period, right? You understand that? If it's full wave, we'd use 800. You know, so no matter what input frequency I give you, if you know that half wave is the input AC frequency and the output ripple frequency is going to be the same. If it's full wave, it's going to be what? Double, then you can use this for no matter what situation you get in. So if you go over to Europe, you could do this. What's the frequency over Europe? 50. In some countries, by the way, you can look at a frequency chart and see which ones are 60s and which are 50s. And there are some companies that have both 50 in a certain region and 60 in another. So what we need to know here is we need to know how much current the load is going to pull. So this is going to be the load current, right? And then this is going to be farads, right? I'm going to run out of space. No, I'm sorry. This is going to be the frequency. And then this is going to be farads. Now, capacitors are usually rated in microfarads and picofarads. Are we okay? So what would be the vote? What would be the DC? What would be the volts DC? No, that would be this formula right here. Yeah, so here you'd have to know the period. Now, over time, 60 cycles, we got that down. Most of y'all should have that. 8.3 for, 8.3 for full, right? 16.7 for half. But the problem is, if you ran into 50 hertz, then you'd be screwed, right? Understand? Or if you, like I worked on my airplanes, it ran at 400 cycles, I would be messed up because, right? You understand that? So my voltage DC is going to be equal to V peak out minus V ripple peak to peak divided by 2. Very simple formula. Y divided by 2, because the DC average is going to be down the center of that ripple. Everybody understand that? Yes or no? So this formula up here, which one are we going to have problems with? By the way, if you want to solve for C, what would you do to rearrange that formula? If you was designing a power supply, what would you do to rearrange that formula? So you're trying to solve for what size capacitor you want in your power supply. So all we have, yeah, so we'd say, we just swap these two, right? I of the load divided by V, what V ripple peak to peak we can get by times L. And there you solve for your capacitor. So what you need to do is you need to know where you want to regulate at, right? You understand? So we make sure that we regulate below the V ripple peak to peak, right? You'll understand that. We'll look at that when we get into regulators. And what load do you want your capacitor to be able to handle? So now you got a formula when you design your power supply, how to calculate what capacitor you need. You need to go up to at least the next standard value. Usually we double it. So if you calculate 25 microfarads, then we'd go up to the next standard value, like 50 or something like that, right? Yeah, it doesn't hurt to put a capacitor in there too big. It's just that it costs more. So the more farads the capacitor can handle. So what determines the cost is how many volts that thing can store up to, right? The working voltage. And of course, how many coulombs it can handle. So you might get a 100 microfarad capacitor that's like this, and it's rated at 25 volts. And you might get the same capacitor as 100 microfarads, and it's that big, and it's rated at 200 volts, right? Understand? So they have to get the plates further apart. Are we okay? Lost anybody so far? So this formula up here, which one we're going to have problems with? So I know C, because that's going to be provided to me. I know L, that's going to be provided to me. Where am I going to have problems at? Out of the load. So I'm trying to calculate the ripple voltage. And so, by the way, everything we do is basically approximations, right? And what we're trying to do is trying to get an answer close to, so we know if it's working right or not working right? So I've got this right here going on. So that, what do I know? Which one do I know? I don't know this value, but I know this guy right here. We call that what? We call it V peak out. So that's on the other side of your diodes, right? We know that. We know that, right? And there's going to be almost hardly, if we calculate our capacitor right, and all we're trying to get is just get an idea of what the current might be, right? We know it's going to be lower. So normally our estimation would be out of the load. All we use is V peak out over R. Now we know it's going to be less than that, right? You understand? But this is going to be close enough for what we call approximations, right? Y'all understand that? So we'll use V peak, we'll use that up there for load current, C and L. Our V ripple peak to peak is going to be, it's actually going to be a little lower than what, it's going to be a little lower than what we calculate. Because our current is actually going to be where? It's going to be in here somewhere, right? You understand that? So we should measure a little bit higher than what we calculate. You don't understand why? But it's going to be what? It's going to be close enough so we can tell if we got a problem, right? That makes sense? That's the load, yeah, all of the load. So this gets us through filters, right? So basically, this is just a rule of thumb. You know, if you come over here and you measure this RMS value coming into the transformer, and you convert that to DC, what you can see is your average voltage should be slightly less than just VP. real fast troubleshoot, right? We know it's going to be less because we didn't take out for the rectifier drop, right? And we didn't calculate the V-ripple DC. Well, we should have a pretty good idea of our output, what it's going to be, just by taking my meter and measuring what. Measuring our RMS voltage in, then come up and do what? Calculate V peak. So V peak would be what? VRMS divided by 0.707. Then we know now I'm going to come over here and measure my DC. Make sure you put your meter on what? DC. Over here, make sure your meter's on AC. And then it should measure less, but not that much, less than what you calculated. That makes sense? That's a good rule of thumb without having to do all the math. Okay? By the way, looking at this output is very, very important. So one of the things we do when we troubleshoot a power supply is, first of all, we look at, if we know what the output voltage is supposed to be, and it's lower than what it's supposed to be, what could cause this to happen? Huh? So let's say we calculate an output voltage, or we expect this output voltage, and we measure it, and it's going to be lower than it was supposed to be. And what things could cause that to happen? The capacitor could be leaky, right? Or it could be open. If it opens, then it's going to be really low, because then you come from unfiltered back down to pulsating DC, right? You understand? So if you get a really low output, that's a good thing. Your capacitor could be open, or it could be leaky, which means it turns into a resistor instead of a good capacitor. So that's good. If it's really low, if it's slightly low, or not really, really low, then what could cause that to happen? Well, we could have lost the diode, right? You understand that. If we lost the diode, then any full wave rectifier, if you lose a diode, it turns from full wave to what? Halfway. So now your capacitors are going to have to run the load twice as long. So if one of the diode opens. If the diode shorts, and that's the problem we have with solid state devices, they can short, or they can open, or they can become what we call leak. Okay. But if they short, it's going to blow a fuse. Hopefully it blows a fuse. If it don't blow a fuse, it's going to burn something off. If it opens, then if it opens in a half wave rectifier, then your output goes to 0. Right? You understand? If it opens in a full wave rectifier, then what you do is you turn a full wave into a what? Half wave. Which means your output, your ripple voltage is going to go up because the capacitor's got to run the load for 16.7 or about 17 milliseconds now, right? You understand? So it's going to discharge, which will cause your output to go down lower. It's not going to be much, but it's going to be lower, right? You could have a faulty transformer. You could have a shorted winding in your transformer. Y'all looked at that magnetic wire? Y'all seen magnetic wire? The orange stuff. The insulation is extremely thin because it's trying to get really good coupling between the wires, right? You understand that? Transformers vibrate. Which means that if they don't tie those things down really, really well, then those wires vibrating together might do what? Might wire that insulation out and they'll short. As soon as you short two windings, then usually it cascades after that, but it'll cause your turns ratio to change. So you'll get a lower turns ratio on the output. So this is where you would actually measure the output of your transformer to make sure it's giving you at least the voltage that you want, right? You understand that. And what's the next thing that could be the problem? So an open diode, which would make it really drop down, right? You understand. Could be a shorted wind, could be an open diode, could be a shorted windage in your transformer. Or it could be you're just trying to pull so much load, you're trying to pull too much current load. So instead of your load pulling 1 amp, and now it's pulling 2 amps, which means that discharge, you designed it for 1 amp, you chose a capacitor for 1 amp, and now it's trying to provide what? 2 amps, and it's going to discharge that. So that means your load is trying to pull too much current. And that's hard to find, guys, without breaking the circuit and measuring. So these guys are pretty, so we looked at this, right? You okay? Ripple voltage, everybody okay there? Yes, no? Okay? And then the slope, this would be half wave, this would be full wave. So what it means is I could use a capacitor half the size for full wave and get the same output voltage, right? Which means it would be cheaper. Ripple voltage peak, are we okay there? And here's our formulas we looked at the other day. Where? This one? Okay. There it is. What do you mean? The capacitors are in parallel with the load. Oh. They do have a you'll run into this every once in a while, where we come over here and we have a lamp, and then they come over and do something like this, and then they'll have a diode with a switch in it. No, that wouldn't work. Oh, I'm sorry. So they have a diode like this, and then they'll have a switch in parallel with it, something like that. And then they'll have it go to a lamp. We set up a circuit where we had some switches. It was really, really neat. And I wish we still had it around here. We had 2 switches that were in series. And then we had 2 lamps out here. Like this. Close one of the switches, one of the lights would come on. If you close the other switch, the other light would come on. If you close both switches, both lights would come on. Right, there has to be something in the circuit, right? So what we do is we'd come over here and we would do this. If you look real close on the switch, you'd see little wires coming out from inside the switch. And so we had a diode right here. Now I like to think about this. And then we had a diode right here. And then we had 2 diodes over here. So right now, there's nothing that could get through, because on the negatives, this would be forward bias, this would be reverse bias. So if I had those switch open, right, you understand that? It wouldn't work. If I close this switch, then the positive alternations would get through. It would go around this one. It couldn't, I'm sorry, I forgot that. It would go around this one, but it couldn't go, I'm sorry, it couldn't, if I close this switch, right, you understand, then the positive would get through. It would bypass this one, couldn't go that way, and it'd go through that light right there. If I close this one, but you hit them. So if you looked at the light sockets real well, you had these diodes, but we would freak people out in DC. Because to them, all they saw was 2 switches in series, and 2 light bulbs in series. So it looks like if you open one switch, both lights would go out, right? But this is the way this works. So if you close both switches, both lights would come on, but they wouldn't burn near as bright. I can't remember 25 watt bulbs, but it was a really neat circuit. So this is doing the same way. So this would be my AC. So with the switch closed, then we'd get full voltage across the light bulb, and it would burn real bright. We open the switch, then we get V peak over pi. I'm sorry, we get V peak over pi, right? And the light bulb would dim down. So this is a real cheap light dimmer. But you only had 2 stages you could go through. You had it wide open or half dim. That might be what you're talking about. And that's just a little circuit. But as soon as I saw that, I remembered this circuit. And we had it hooked up on a board, and somehow it disappeared. And that took a lot of work, guys, hiding those diodes so people couldn't see them. So y'all can see that circuit. You can really screw with people in DC's mind. It's like when you get into AC and you start dealing with capacitors and inductors, you'll actually get more voltage drop in a circuit than you have applied to it. If you hadn't had AC yet, you're going to. So you can come up and measure, you got 50 volts applied to the circuit, and you measure across your resistor, and you got 30 volts, and you measure across your capacitor, and you got 30 volts, and you add them together, you get 60 volts, and you're saying, but I've only got 50 volts applied. That messes them up too. Well, that's just a shunt. We could do little circuits like that all day long. Yeah, but still, it's still going to be a regular. But we got to put a resistor right there. Why don't we got to put a resistor right there? Because at forward biases, it's going to mess it up, right? So what would happen is when this is reverse bias, then you have this series circuit, right? When this is forward bias, this guy right here is shunted across. So you switch from a circuit that looks like this to a circuit that looks like this. So what happens is on your positive alternation, you bypass the second resistor. So what we would see across this guy is we'd see this right here. And what we see across this guy is we'd see this right here. See, that's it. This would be the output voltage. Because the positive alternations are what? Bypass. And we can do little circuits like that to get strange signals out. How do you find current? To which resistor? It's halfway. So first of all, you'd figure VP, what would it be? Halfway, VP over pi, and then you divide that by that resistor, and that would give you the current flow for that. What's that? V peak over pi. Halfway, right? Yes or no? Average DC for half-wave. Full wave is 2 V peak over pi. Half wave is V peak over pi for the average DC. Makes sense? And here you probably ignore the diode drop. Here it would be plus 0.7. Okay, Milton? Or are you still kind of confused? Huh? Okay, so I come over here and I put 10 volt peak in or RMS. Okay. Over here, that means I would have 5 volts peak. I would take that, divide it by 3.14. Then that would come up and give me my volts DC. I'd take I would be equal, if this is called R1, then I would say I would be equal to my volts DC divided by whatever R1 was, like 1K or something like that. It's the same formula that we use. It's just here the diodes in parallel. So what happens in the positive alternation? When the positive alternation comes through, it's shunting through here. This guy here on the right? That's not what we're asking for. In the negative alternation, you only take out the 7/10 of the load. In the negative alternation, this guy is reverse bias. And what you get out of here, you get negative voltage. So your output would actually be, there's no such thing as a negative current and positive current. So you can use the absolute value right there. But here they're just doing a little different. Just to do what? Daze and confuse you, but it's a good question because if you understand the operation of a diode, then you should be able to figure out what goes on no matter how we put the diodes in the circuit, right? That makes sense.
So once you get the answer from 5 divided by 3.14, you put it into that other problem and you get the answer.
Yeah, all we're doing, we're adding one more. We're not even changing any formulas. These are just our formulas. What we got to do is we got to figure out what type of signal I get across the output. So here we have to put a resistor there, right? So this is a standard circuit, right? And you'd have no problem with that guy right there. But the problem is we come over here, we put a second load right here. Now here we have, so when a positive alternation comes through, then what does that do to this diode? 4 biases, okay. So what does it drop? 17. It's a parallel circuit, right? So if it's dropping 7/10 of a volt, what's across the load? 7/10, okay. But we're not using that because it's not enough to fool around with. Now on the negative alternation, when this goes negative, what happens to this guy right here? It reverse biases. So now whatever's across here is going to appear where? Across the load. So it's going to come up and give us this right here. And it's going to be the full peak voltage because the diode is blocking, right? It's not conducting. So how do we calculate the average DC for something like that? Volts DC. How do we calculate the average DC for something like that? Or here it's going to be just VP because we're not going through a diode, right? VP over 5. Now that gives me my average DC voltage, right? You understand that? Huh? Well, if the power source is DC, then if you reverse bias it, you get the full voltage. If you forward bias it, then you get 7/10 of a volt. So if I came over here and did this, I took away my DC and I put it like that, would that be forward bias or would it be reverse bias? Okay, it's forward bias. What would we have across the resistor? Well, not reference from here. This is positive. It's always going to be positive, but it's going to be 0.7. Yeah, here's your positive supply. And when you measure across the diode, you're going to be measuring relative. You're going to put your black lead right there, right? So your black lead is going to be toward the negative. Your red lead is going to be toward the positive. So it's going to be a positive 7/50 volt. Now, if I come over here and swap the if I come over here and turn the thing around, okay, it's going to be what? It's going to be reverse bias. So this guy here is going to turn off. So what's this going to go to? This is going to go to whatever DC voltage we put over there, right? You understand? Well, that's not true. That's not true. So we need to think about this. So if this is a 1K, and this is a 1K, and this DC is 10 volts, then what I would get over here is I get 5 volts. So that's something that I forgot about. So that would, what we showed you a while ago wouldn't be quite right. Because we got this right here. We got, so now, so let's redraw it. This is what we call a series circuit, right? You understand? And the diode's turned off. So it's acting like a series circuit. Okay? Understand? So, if I come up here and put 10 volts right there, will either one of these resistors drop 10 volts? No, notice we got a problem. It's going to be proportional to the size of the resistors, right? So if they're the same size, then they're going to drop the same voltage. So that means across this guy I would have what? I would have 5 volts. But you would calculate it just like you would a series circuit. Now, if the diode is forward biased, then the circuit changes. So that would generate a neat signal. So if we forward bias it, then basically we end up with this circuit right here. So now all my voltage will be dropped across the resistor. So what we'll end up with, if you looked at it with an oscilloscope, if we could look at it with an oscilloscope, then this guy here is not going to drop the full voltage like we talked about a while ago. So Rich made a mistake. Go ahead.
Forward bias.
There's no parallel circuit here. It's either, if the diode is forward biased, then we end up with a 1 resistor series circuit, right? I'm sorry. If it's forward biased, we end up with a 1 resistor series circuit. If it's reverse biased, we end up with a 2 resistor series circuit. So this would be the equivalent circuit. So if it's forward biased, we end up with this, right? If it's reverse biased, we end up with that. There's no parallel circuit. This guy here is acting like a switch. That's all it's acting like, a switch, except it drops 0.7 of a volt. So how you hook control devices does not determine whether it's a series circuit or a parallel circuit. It depends on how the loads end up, right? That makes sense? So we switch from a 1 resistor circuit when it's forward bias and a 2 resistor circuit when it's what? Reverse bias. So good question. That's a good circuit, guys. So a while ago I said we get the full peak voltage. That's not true. When it's reverse bias, we get the 2 resistor series circuit. By the way, when we have surge current, if a rectifier circuit, if a capacitor is connected across the load, the capacitor appears as a short. At the instant the switch is closed, the sudden surge of current can damage the diode, so a current limiting resistor may be used. We usually don't have to worry about that because if we use a rectifier diode, so the diodes that we're using, these are 1N 40 something. And this thing here, these are 1 amp diodes. Do you think when you first throw power that thing gets 1 amp? No, it don't. But it's got a 1 cycle surge current of 30 amps. So we don't have to put a resistor in here for that thing, because it can, those diodes can handle that when that capacitor originally does what? Charges. So I haven't seen one with a surge current in there a long time. I have seen power supplies where they put a dual switch on here, so they have a mechanically connected switch, and then they'll have a resistor across here. In fact, my power supply is like this. and then your power switch and this guy here are connected together. So when this one's closed, this one's open, and when this one's open, this is closed. So it'd be like a, now why would we want to do something like that? So this guy right here definitely doesn't have it. Turn on. See the nice red light? What's this? What happened? Well, no. It's got a discharge of big old capacitor. It's got them big old capacitor. What's it discharging? Now, if I was to hook a load up out here, then it would discharge this. But if I got a power supply like this, that I don't hook up to a load all the time, then if we had this circuit in there, when I turned it off, it would automatically discharge the capacitor. Electrolytics, we don't like to discharge. I mean, you'll see people use screwdrivers because a lot of them will be big old radial lead capacitors. These will be big old capacitors in a power supply. And your terminals up here will be screws. Wake up, Anthony. Anthony. Wake up or stand up. And you'll see people take screwdrivers and they'll put it across the capacitor and short them out. And that's not good on the capacitor. You've got a $50 capacitor in there, and you're going to limit the life down. So a lot of times they'll actually put a big resistor across here to give you something that discharge that. Because if you don't have a load hook up to that sucker, then you see how long this guy right here takes to actually discharge those capacitors through its internal circuitry. So I won't have a resistor. But if I was to put a load across here, you'd see that the discharge was a lot faster. This is the problem we have. So right now I turn this thing off. I have this thing set up for up to 30 volts, right? You understand, across the two terminals. And I turn it off and that 30 volts is still there for a while. A pretty good deal of time. So you build discharge circuit. So the power supply that I build, I have a discharge circuit in it. So I turn it off and you'll see my light goes off instantly. Okay, y'all guys go ahead and take a break and then we'll look at regulators and then we'll try to start working on our lab. We have a lab where we check diodes out. It's a handout lab, but when I looked at it, it's not ready. So we'll skip over that one. And these figures can definitely not be right. At is a special diode called a Zener diode, but we won't get into that today. But this is the 78. That's the high current version. This is a negative regulator. We can probably look at this. And sometimes they'll give us the actual internal circuitry of the actual regulator itself. So there it is right there.
saying that bridge was.
But this is the guy we're going to look at next. This is called a Zener diode. Can y'all see the symbol? Does it show up okay?
It's kind of like circuit line.
Yeah, well, sort of.
On the dial,
So the actual symbol, if I was to draw it up, if I can keep it from zooming in, is it looks like this. So it's got the basic arrowhead like this. But what we look at is the cathode comes up and looks like that. And these are regulator diodes, guys. So this, you see, even though we don't see it, this is going to be, every regulator I've ever seen, this is the basic that actually sets that. And these are all different types of symbols. But the problem is, I don't need to worry about this. All I got to do is figure out, what does a regulator need? Well, it needs the input unregulated, it needs an output for regulated, and it needs a common, right? You understand? So these are all what we call three-terminal regulators. All you got to do is figure out what their current is rated at and what voltage they're supposed to regulate at. That make sense? So the one that they talk about is the LM7805. So the 7800 series is positive regulators, and then the 7900 series are negative regulators. Oh, I know what's going on. So this is a typical 7800 regulator, and what they do is the last numbers indicate what it's going to regulate at. So a 7805 would be a positive 5-volt regulator. A 7812 would be a what? 12-volt regulator. 7815 would be. And all the 7800 series are positive regulators. The 7900 series are negative regulators. So a 7905 would be a negative 5-volt regulator. So we'd give it negative DC, unregulated in, right? So it don't convert positive to negative. We'd give it a negative unregulated in, and then it would regulate it. These are packages. So these things come in a 3-pin pack. They're all depending on it. I'll show you. We call these PO packs. So I think this is PO 2.2. This is PO, I can't remember what it is. But basically, it depends on the current rating. So the bigger the package, so you might get a 7805 rated at 100 milliamps, and it's going to be in a little small package. You might get a 7805 rated at 1 amp, and it's going to have to be in a bigger package. But all we see is 3 leads, because we have unregulated in, right? You understand? So we have unregulated in, and we have regulated out, and then we have common. So unregulated in, right? Then what this would do is be regulated out, and then this right here will be our common, which they call ground, but it might not be ground. And they come in surface mount. You might see them on the printed circuit board, surface mount. Surface mount devices. PO3 packs, PO2.2, PO92. I think these are the ones that we have. This one I think it's rated like 100 milliamps. These guys are rated like 1 amp. These guys are we have one of these. We have a 7805 H05 in our trainer. It's rated at I think 5 amps. But they're still pretty easy to understand. And you don't have to understand what's inside of them. You just need to know how they work. If they don't work, you don't get inside there and place a transistor. What do? You replace the whole device, right? You understand that? So we don't need to understand how that internal circuitry works. All we got to do is know what it does. But we'll look at a Zener diode. That's the first regulator we're going to look at. And you'll still see these guys used all the time. But these are really, really neat. And then we have variable regulators, which are 3-terminal regulators. But the way they work is they'll come in and we'll put 2 resistors right here. And then this right here will be variable. And then your common lead connects right there. And these are variable regulators. keep getting them screwed up. We'll look at them. So this is what the trainer uses. So the fixed regulators, it's going to use the 7800 series or the 7900 series, right? And then it's going to use an LM, and I think we showed y'all the schematic for the trainer, didn't we? I keep going through this. So okay, we call them fixed regulators, which means what? You can't vary the voltage. They're going to give you a certain, if you give it the right input, they will give you the right output. So here's the trainers. Here's the transformer we're going to be using. So this is the 12.6 center tap transformer. They got it kind of labeled weird because I got 6.30, 6.3. But it's actually a 12.6 center tap transformer, right? And it's totally isolated, so notice ground is not referenced. Whether these power supplies, if this is a common, I will have to check it. It does have a chassis ground right here. If they've got this connected to that, I don't know. Y'all know you lose ground. You got ground on the primary side of the transformer. You lose it when you come through the transformer because it's magnetically coupled. So if you want the output of your secondary to be referenced to ground, you have to ground it, right? Y'all understand that? So this is our plus 5 volt regulator right here. 7805, but it's a 8 series. It's like a 5 amp regulator. This is the little LED that comes on. Here's our filter capacitor. They got 4,700 microfarads, 16 working volts. Y'all understand that now, right? Which would probably be at least double of what we have right there. There's a 7912, so what's the 7912? Negative 12 volt regulator. And over here, this is where that terminal that sits up. It's labeled negative 12, right? Okay. Here's the actual main filter. These are just what we call these are small filters. They give you the size that they want you to do on this, just to prevent the thing when it regulates and it's trying to move around where it don't get really big. This is a 22,000 microfarad, 25 volt capacitor. And we got the same thing up there on the plus 12. That's a 7812. That's a what? 12 volt regulator. So we're not actually seeing this guy discharge. We're seeing this 10 microfarad discharge. This is a multi-winding transformer, right? Okay, there. And that's it, guys. These are, so there they are. So the LN17, this is the variable positive regulator. The LN337, that's a negative variable regulator. Here's our feedback resistor. There's that circuit that I showed you. We have regulated in, right? We have unregulated in. We have regulated out. We have our adjustment. Are you okay? These are all fixed. These are variable regulators. So the odds are, the standard power supplies that we normally lose, we see plus 12 all over the place. We see minus 12 all over the place. We see plus 5 all over the place. That's basically what we power up digital logic with, and then 24 volts. So odds are these standard DC power supplies that's out there, odds are you're going to be able to find a fixed regulator that does that for you. So all you got to do is come up with the right watt. Make sure you use the right transformer to get what you need. Right? You understand? Make sure that you have the diodes that provide the current you need. Be able to choose the right capacitor that prevents these things from getting into that deal. So what we have to do is we have to make sure that we give that thing enough voltage So that dip or that valley does not get into my regulation. You understand what I'm talking about? So that means if I come over here and I've got this unfiltered DC that's changing with current, right? It's changing with load. Then my regulator is going to have to regulate down in here. Because if this ever gets down and dips into my regulator, then we got problems, right? You understand that? So that's why you got to figure out, make sure when you figure your ripple voltage for that current, that it never drops into where you're doing what you're trying to regulate. Does that make sense? Yes or no? Yes? No? Make sure the ripple voltage doesn't drop into your regulated voltage. Huh?
I thought that's what the regulators do.
It can't get out more than you do, right? It can't get out. If you don't give it the voltage that it needs, it can't add voltage, it can take away. That's all the regulator does is clip it off, right? Understand? It can't take care of the ripple voltage. The ripple voltage is decided by what? Two things. What determines the ripple voltage? Well, three things. The size of the what? Capacitor. The load current. And of course the frequency, but usually the frequency on our power supplies over here is set. The frequency of the input. So those three things determines how far this valley goes down. So I can always clip that off, right? You understand? So if this down here is 7 volts, if this right here is at 7 volts and I regulate it plus 5 volts, I'm okay. But if this ever comes down there and I don't choose the right capacitor, right, or if I try to load it down too much, as soon as this gets down to there, if I was to look at my output, it'd be set at nice, pretty 5 volts, and then it would dip right there. Because it can't add voltage, it can do what? It can strip it off, and that's what a regulator does. It regulates below below the valley of the ripple voltage. The top one, we have no problem. So what determines how fast that thing slopes down would be what size capacitor, right? You understand? We'll leave the frequency off for us because our frequency is always going to be what? 60 cycles. So the size of the capacitor, and then also how much load you put on there, right? So the more current load you have, those valleys start dropping down because the capacitor discharges faster. And if it ever dips down below where your regulator's regulating, it can't do what? It can't regulate anymore. It's just like you got your cruise control on your car and you go up a hill like that. Once that gas pedal goes all the way down and now your car can't do that, then your speedometer is going to do what? It's going to slow down because you've dropped out of the range of it can do what? It can regulate that speed. So a car cruise control is a perfect example of what a power supply can do to you. So you can't add more gas than your injection system can throw into your ignition chamber. Yeah. Once you've met that, then the car's going to do what? It's going to slow down. Yeah. So that's it right here. So that would be like the hill. So as long as I'm running up and down hills like this, we have no problem, right? But if I get to that hill and it causes that thing to discharge, and it gets down in there, then we go out of regulation. Our output voltage would actually drop down because now it's, instead of being 5 volts, it's going to be some type of average, right? So that's why it's very important to choose that capacitor for the right size for the what, the current or the load that you're trying to do. Now the problem is, you say, why don't I just go out and get a 50,000 microfarad capacitor? Well, 50,000 microfarad capacitor is probably going to cost you $30, right? When you need a 1,000 microfarad capacitor, which you could probably get for $2. So if you design power supplies and put a capacitor in there that's too big, then you're doing what? You're wasting a lot of money. So we okay? Everybody okay? We got. I'll give y'all during the weekend, but one of them's for unfiltered, unregulated power supplies, and the other one's for filtered, regulated power supplies. So what's our next lab? No, I think we do unregulated. unregulated.
Rectifier circuit.
And we're gonna use the, we're not gonna give y'all transformers, even though we have them. You're gonna use the transformer that's on the wall, on the trailer. Everybody okay? That isolated transformer, 12.6 volts. So you'd get 6.3 volts across the center and one outside, right? You understand? And if we use a full wave center tap, we're gonna use both sides. So your math will be around 6.3 volts. I think for your full wave bridge, I think you go all the way across the thing, if I remember right. I can't. So what lab number is this, guys? Yeah, it should be the next one, shouldn't it? So we're not going to need the transformer because the transformer is part of our trainer, right? Is this third? Oh, this is not. This is D lab book. We're going to use a 4000 series. I think it calls for a 4001, but if you've got a 4002 or a 4003, y'all understand. The only thing that changes is the breakover voltage. All of them's the same. These are going to be in a plastic pack. They're rated at 1 amp. So it calls for a 4001, but you understand if you got a 4002 or 4007 or 4005, it's fine, right? You understand that? Everybody okay there? 12.6 volt center tap transformer, we're okay there. Fused, it's fused. It's fused in the trainer. So we got that, right? Now what you're going to do, this is going to be a half wave rectifier. You're going to use an oscilloscope. How many people think are using an oscilloscope? Then everybody, okay, then we're fine. Normally what we try to do is try to put somebody that hadn't used the oscilloscope into somebody that has. So we're going to have to use both channels on our oscilloscope. One of them's going to be across the load, one of them's going to be across here. We can't measure across the diode because, remember, the black lead on the oscilloscope is ground, right? So we can't probe inside the circuit. Any questions on this guy? So up here, you're gonna draw the secondary voltage, right? And this is going to be AC. Over here, you're going to draw what you get across your load. Over here, you know you can shift your reference over here because it's DC. You need to make this match that, right? You understand? Yes or no?
But they're gonna be channel 1 or channel 2? You know,
Relative to, it's up to you. Now, they call, they say channel 1 is going to be across the primary. And they say channel 2 is going to be across the load. But up here, they don't say channel 2 or channel 1, they say secondary and load. So what that means is if you hook channel 2 up across the secondary and channel 1 across the load, it's not going to make any difference, right? It's just that whichever one, you need to probably, well, you can actually trigger on either one of them because they're going to be the same, right? Are you okay? That makes sense? So you can follow this right here exactly, but you don't have to because up here they don't identify the probe. So what we're saying, you're not going to come over here and draw your AC signal like this. And what we'd like to do is just get at least two cycles, right? So how many? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2 cycles, we would go. So we'd come over here like this, right? 1, 2, 3, 4, 5. I'm sorry. 1, 2, 3, 4, 5. I'm not doing that. And then 1, 2, 3, 4, 5, right? Are we okay there? And then over here, you need this to match, right? So is this a positive power supply or a negative power supply? we look at the diode and we see what's pointing back toward the source. If the anode is pointing back toward the source, it's positive. If the cathode is pointing back toward the source, it's negative, right? And then over here, you don't have to keep it centered up. You can if you want to, but you could actually move down here. But we should come over here and do this, right? It should look something like that. Right? Are you okay? Yes or no? Then what you're going to do is you're going to take a 100 microfarad capacitor, and what you're going to do, and what we're going to do is we're going to do this a little different. We're going to add, like I said, I can't find my lab book that's corrected. And this, you need to, first of all, let me bring this up. So first of all, you need to mark that out. This don't make sense. No, we're going to mark out this guy right here that says P. That's going to be P across the load, right? It's not going to be peak. It's going to be what? What you figure out is supposed to be. Now, the first thing you're supposed to do is what? The first thing you're supposed to do is compute it. Right? And then you're going to do what? Measure it. The only thing that they don't do is I want you to add this, is I want you to compute the V ripple peak to peak. This thing is lagging behind me, so it's going to be kind of, so I'm writing in V ripple peak to peak computed. And then we'll come back and do what? Measure it. We need to compute this over too. Sorry. We need to try to figure out, so this is going to be V load what? Computed to. Sorry guys, can y'all read that? It kind of gets me delayed. And then we'll do the same thing on the rest of the power supply. So we're going to compute it, then we're going to measure it, right? You understand? And this first of all, it makes sure you know how to do the math, and plus of all, it verifies if your power supply is working correctly. Okay? I don't know if they've got any troubleshooting. Then we're going to do the same thing here, right? This is going to be a full wave center tap. Are we okay? And down here, you're going to add two more charts down here. Compute the ripple and compute the load. Right, okay? By the way, what should your ripple frequency be right here? Full wave. Of course, here our secondary is going to be 6.3, but remember that 6.3, odds are it's going to be a little higher because we're not fully loading the transformer, right? So what they want to do for your math is they want you to do what? They want you to measure, right? Okay. And then then we'll put a 100 microfarad capacitor across that too, see how it jumps up and how much of our DC pops up there. And then we go to a bridge rectifier. Now the problem we have with a bridge rectifier is we can't look across the transformer. Why can't we look across the transformer? Because the ground is on the other side of the diode, right? Or the common's on the other side of the diode. So we can't look at there. You could, but what you're going to have to do is be real careful. Only use one scope probe. Don't have two hooked up, right? You understand? You know, since we're isolated. So we're isolated. So what you need to do is you need to make sure this guy right here is gone, right? You understand that? And then you can come over here and do that. But I don't think they ask you for the secondary vote. I don't think they do. No, what they do is they ask you to measure it, but this is in what? This is in what? This is an RMS. Everybody okay? Don't forget your what? Conclusions, right? And then you'll do these as a team, right? You understand that? But you do your conclusion and you do these questions. These are yours. These are not team effort. Are you okay? So ready? So I'll go get your worksheets that y'all going to turn in or during the weekend. Give y'all something to do during the weekend. I know y'all's looking forward to that, right? And then